Hello, it's great to have you joined us. We are really excited today to talk about the topic power saving on portable devices with i.MX 7 ULP, 8 ULP with you guys. My name is Holger Fröhlich from F&S Elektronik Systeme in Germany. I'm the general manager of F&S and work since 1996 for the company. With me is my colleague Patrick. Before we start, I want to show you in one slide what F&S stands for. F&S is a privately held company located in Stuttgart, Germany. We develop and produce embedded modules based on the newest NXP application processors. Since 1996, we offer different product families. We offer single-board computer product family in form factor Pico ITX. Besides single-board computer, we also offer system on modules with plug connector, Goldfinger connector, or as a BGA solder module. All our development and production is certified for industrial as well as medical customers. Today we are talking about our solutions for low power devices, including handheld devices. On this slide, I have to try to show you where low power devices are positioned within our PicoCore family of products. On the left, you see our module based on NXP i.MX 8M Mini and i.MX 8M Nano. The module is best suited for application where high computing performance is needed. The module is available with Wi-Fi Bluetooth and 1 gigabit Ethernet, or as an option with 2 gigabit Ethernet interface. In the center, there's our module based on NXP i.MX 8M Plus. Main difference is more industrial interfaces like CAN and LVDS, and a neuronal processing unit for HI edge computing. On the right, our module based on NXP i.MX 7 ULP. This module is especially designed for low power handheld applications. After this short introduction, I want to hand over to my colleague Patrick. Patrick is senior software developer at F&S and has deep knowledge in the 7 ULP solution.
Yes, thank you, Holger. So let's go to the next slide. We will talk first about the 7 ULP, as Holger mentioned. So first of all, I want to show you what about the 7 ULP core itself. So we have on the one hand a Cortex A7, you can see it on the left side, and on the other side we have the Cortex M4. So the Cortex A7, therefore we have a rich operating system support, which means you can use it as a performance core. You have there a Linux system like Buildroot or Yocto on it running, and on the right side we have the Cortex M4. The Cortex M4 can be used for real-time operations. You have there a real-time operating system like FreeRTOS, but you also can use a bare metal application on it to get real-time performances on this core, and we have also the possibility with different power modes where the Cortex M4 can control these modes.
Okay, so I see it's a heterogeneous multi-core processor. So can you give us a more detailed overview over the 7 ULP?
For sure. Let's go to the next slide. We have on the right side a block diagram of the 7 ULP. So in the upper half of this block diagram, you have the application domain, and in the lower of the block diagram, you have the real-time domain. This is pretty new for the 7 ULP and for the cores, because we have there two different kind of domains. And the special feature of these domains is also that we have separated interfaces on it. So you can see it at the upper right and at the lower right in the blue block. So the application domain has its own interfaces like I2C, UART, and SPI. and also the real-time domain, so the Cortex-M, also have these interfaces. So they are completely separated and can't be accessed by the other domain. In the middle of the block diagram, we have the clock and power management. So the clock and power management can be accessed by both domains.
Okay. So Patrick, what do you think? What are the most important features or differences, yes, to other application processors?
Yes, we have here 3 different points. One point is the separate power domains, which I explained before. Another thing are the boot modes. And the third thing is the independent interfaces. So I will go deeper now. What do I mean with boot modes? So we have here, you can see different kind of boot modes. Normally we know from the i.MX8 family or i.MX6 family that we have just one boot mode. So, and this boot mode is normally the single boot. This means the Cortex-A7 is the primary core and the Cortex-M is the secondary core. So, but we have here 2 other boot modes. And the next boot mode is the dual boot. Dual boot means that we have a simultaneous boot. So both cores boot at the same time. And the Cortex-M4, this is special, can be the primary core. This doesn't work before. The Cortex-A was always the primary core, we can't switch the roles. But now it's possible to switch these roles. And another benefit of the dual boot is that we can use execute in place, which means the boot code for the Cortex-M is placed inside the SPI NOR, and therefore we have a bigger size of the code, because normally we can use a TCM. It's just about 32 kilobytes of space, but with this execute in place special can be boot up to 4 megabytes. And the last boot mode is the low power boot mode. So the low power boot mode means that the Cortex-M4 is the primary boot core and it just runs solo. So the Cortex-A7 is not booted yet and the Cortex-M4 can start the Cortex-A7. Therefore, we have the possibility to save a big amount of power if you just don't boot the Cortex-A7 and first boot the Cortex-M4.
Do I right understand that so these different boot modes in combination with splitted power domains, that this is one of the biggest improvements now?
Yes, for sure. So because the Cortex-M has the possibility to shut down the most amount of the voltages of the Cortex-A7, so the Cortex-M just run by itself and only power up the single periphery which are needed, and so we can save a big amount of power.
Okay.
So maybe here we can just go for the different kind of domains. So compared with an i.MX8 so maybe then it's a little bit clearer for us. So on the left we have just the i.MX8 so it's just one domain, an application domain. So we see there is a Cortex-A53 and a Cortex-M4, and both are connected to the same bus. So both have access to the same periphery units, so like DDR, GPU, and other slave devices like I2C, SPI. On the right side we have the 7ULP, and you see we have these 2 kind of domains, the application domain and the real-time domain. So the A7 is connected to a bus system with its peripheral, like DDR, GPU, the other slave devices like I2C and so on. And on the right we have the real-time domain with the Cortex-M4, which is also connected to a special bus and have its own periphery units like slave devices, audio, or the TCM.
So this means with the 7ULP, for example, if I think about UARTs, yes, that there are UARTs for the A7 core, for the application domain, and are UARTs for the real-time domain. So with direct access from the Cortex-M real-time processor system.
Yes, that's correct.
Okay, and beside these power domains and boot modes, are there additional features, advantages, which comes with this new CPU?
Yes, so I can summarize these features. We have, on the one hand, extreme low power modes. So we can go to different stages to save more or less amount of power. Then we have the ability, due to the two domains, that we have, we can shut down the most amount of the silicon, and the Cortex M4 just run, let's say, in idle mode, and everything else is shut down. Then we have a specially designed i.MX, which controls the voltages of the CPU 7ULP. It's specially designed for this CPU. Then, as I explained, the separate power domains with the separate peripheral, and the possibility that the M4 can act as a master, which I explained before with the boot modes. And these features are saving lots of power for the 7ULP.
Okay, so very interesting concept and architecture. And so this is a CPU from NXP, it's a 7ULP, but F&S, I think they have something done more, yes, on top of this. So what is what type of product has F&S built on top of the 7ULP?
So F&S has built a module with the 7ULP. The 7ULP, you can see it, we have different features for the Pico-Core MX 7ULP. For example, LP DDR3 RAM, an SPI NOR for the Cortex M4, an eMMC for the Cortex A7. We also have a Wi-Fi Bluetooth module on it, JTAG interface for debugging. Then we have supply power, either 5 volt or 4.2 volt. USB OTG, UARTs, I2C, SPI. Also display interface, it's MIPI DSI, and an audio codec. Yes, so the most important features is the 2-plug connector with 80 pins each. Then we have the long-term availability of to 2028. Then the voltage supply, 5 volt or 4.2 volt. Then 7ULP is mounted, Wi-Fi, and yeah, we have the module is very small, so we have a size to 35 to 40 millimeters of the module itself.
Okay, so sounds really interesting. So let's summarize, yes, the features of our module and the 7ULP. So on the Pico-Core MX7 ULP, we are using the 7ULP processor for sure, a combination of Cortex A7 and Cortex M4. It runs up to 720 megahertz. And yes, so we have a tested build root and Yocto BSP. Yes. I think this is very interesting for the customers. We offer a real-time free RTOS BSP and have also tested samples for bare metal access, yes. So we have a bare metal library, and included in this bare metal library we have a real-time communication stack for communication between the Cortex A and the Cortex M processor. Also display support is offered from F&S. We can connect MIPI DSI displays, but also LVDS displays as well as RGB displays. Flash memory, you already mentioned.
Yes.
Supply voltage, single supply voltage, but we have different inputs, yes. I think later you will say some words about this topic.
Correct.
We offer the module in two different operating temperature grades. So one is commercial temperature grade. It's from 0 degrees up to 70 degrees. And the other one is from minus 20 up to plus 85 degrees. Yes, the size you already mentioned, and long-term availability. A few words about connectivity. I think this is also important for module for handheld devices. Mm-hmm. So we have a Wi-Fi module on the Pico Core. It's a dual band module, so we have AC support in it. We have also Bluetooth 5.0. The Bluetooth module has a SIG QDID. So in combination with QDID of your Linux Bluetooth stack, it's easy for you to get also a QDID for your product. Certifications, that's important and can be very expensive, but the module is already pre-certified for CE, so for the European Union, but it's also certified for FCC, IEC, NCC, Australia, India, and Japan. So power consumption, I think, so this is the main feature, yes. Of the Pico Core i.MX 7 ULP. Patrick, can you explain, can you say a few words about the power consumption, how low it is?
Yes, so let's take a look at the table. We have here some of the different modes which can be used. We have a high-speed run mode, a normal run, and so on. I don't want to explain all of these modes now, but just for clarification, so we have a normal state of the Pico Core i.MX 7 ULP. You have running the Cortex A7 and also the Cortex M in the run mode. So therefore, we have about 620 milliwatt of power consumption. And the interesting part here for saving power is that we can just go for the Cortex A7, and in the deepest mode, it's called VLLS. And we also can go in this mode with the Cortex M4. And then both cores are in the so-called stop modes and can be interrupted by an external source, for example. And in this state, we have a power consumption of about 11 milliwatt, which is very, very low. Mm-hmm. And I think that's interesting for handheld devices. And yeah.
Okay. So is F&S only offering this Pico Core module, or is there some environment around the Pico Core?
So we have an environment for our customers. So if our customers want to purchase this board, this module, we offer a starter kit. The starter kit contains the module itself. We also have a base board for this module with the different interfaces like audio, USB, and UART I2C, so that the customer can connect external devices. And we also have a display, our MIPI DSi display with 3.5 inch, and a battery for battery supply. Mm-hmm. So,
okay.
I will explain now the battery supply a little bit, or the input sources of the 7 ULP baseboard. So on the left side, we have different kind of sources. It's like just a 5-volt power supply with a generator, for example. Then we have also the possibility to use the USB Mini as input supply, also 5-volt. And we also have the feature that we can just connect the battery with 4.2 volt to power supply this board. And the special thing here is that we just can change the input sources on the fly without the board have to reboot or something. It's just hold the voltage, and so we can just use mini USB, and then we can just connect the battery and switch off USB. So the baseboard has this feature to change these input sources on the fly, and I think that's very special.
on the fly. So the application is not interrupted. We don't have to boot if we switch from the USB, for example, to the battery. So it's still running, yes?
It's still running.
Okay. Okay, so now we show you a demonstration of an application with the 7ULP and also our brand new MIPI DSI display with PCAP patch.
Here you can see our 7ULP demo system. First of all, I will describe the different components. At the bottom you can see 2 buttons and a current meter. In the middle is our module, baseboard and a battery. At the top you can see a 3.5-inch MIPI DSI display. The demo shows a bicycle speedometer. The first feature of this demo is a use case of the ultra-low power mode. Currently, the demo system runs in performance mode. We are riding the bicycle and navigate to our final destination. After some time, we arrive at our interim destination. We stop and there's no more interaction with the bicycle. After some time, the bicycle speedometer goes into deep sleep mode to save power. When our stop is over and we continue our trip, the bicycle speedometer will start automatically at the same point where it has stopped. Now I will simulate this. Let's say we are riding the bicycle and stop at our interim destination. So we just arrived our interim destination. So the bicycle goes into deep sleep mode. Now we see the display went off and the current meter went down from about 160 mA to about 3 mA. So let's say we're having a break and we now want to continue our trip. We see that the bicycle speedometer automatically continues at the same position as it were before. Another feature that we have described before in the slides is our battery management circuit. Currently we have a 5-volt power supply over the green connector. The battery is also connected and charges. When I unplug the green connector, the circuit switches from charging the battery to power supplying the system. The demo keeps running and the input source is being changed without any interruption. Now the battery is our new power supply. Now I will show you. At the moment, the power supply is the green connector. Let's unplug the green connector. And we see the demo still runs and the battery is the new power supply. As you can see, there was no interruption. The system did not reboot or freeze. I hope you enjoyed this demo. We will now show you another demo with our brand new 3.5-inch MIPI DSI display with PCAP touch.
Seven ULP is a really interesting product. However, some applications require more computing power and additional interfaces. NXP recognized this and developed the new i.MX 8 ULP. Patrick, can you give us a first look to the new NXP i.MX 8 ULP processor?
Yes, for sure. Let's talk about the block diagram of the 8 ULP. So on the right we have the block diagram. In the upper of the block diagram we have the application domain. In the lower part we have the real-time domain. And special here is that we have in the middle the low power audio video domain. This is a new feature of the 8 ULP, that we have a third domain which you can use for audio and video. And we also see in the block diagram that it's more complex than the 7-ULP. So we have more interfaces and units within the 8-ULP which we can use. So we also have, as in 7-ULP, different interfaces which are separated for each domain. And this is very interesting because of the third domain. So we expect that we can save more amount of power, and the power consumption will be more or less than 7-ULP. So we can see here the three domains. We have on the left side the application domain with the Cortex A35. Then we have in the middle the low power audio video domain, and on the right side the real-time domain. So the two domains like application domain and real-time domain are more or less like 7-ULP, except we have more interfaces, which you can see on the right. In the real-time domain we have a fusion interface. And in the middle, the special third domain have the possibility to control DDR and the GPU. Mm-hmm. So therefore we can control from both domains the third domain. So we have access to the DDR and the GPU.
That sounds really interesting. But main feature of 8-ULP, I think, is still the power consumption. Are there already some figures available?
Yeah, currently we have here this diagram from NXP, where we can see in the green bars that we have the 8-ULP and the 7-ULP. And what we see from the height of the bars is that this 8-ULP consumes lesser power than the 7-ULP. So we expect that it's, I think, about a third or a quarter of the 7-ULP consumption for the 8-ULP.
So means we have higher computing power because of the two Cortex A35 cores, and also better graphics, but lower power consumption.
Yes, that's the goal. So I would say let's talk about the F&S solution for 8-ULP.
Okay, so I think it's my part because it's still under development. 8-ULP is not released up to now, and so, but yes, as already mentioned, low power consumption for battery power portable devices. This is the main focus of the 8-ULP. Therefore, the development goals of the F&S 8-ULP solution were smaller size and thinner. The result of our investigations and our development is now a module with the size of 35 by 35 millimeters and LGA contacts. So we don't have any connectors. The module will be directly soldered on the carrier board, and the module is very small. For sure the module is long-term available, like the CPU2. We have display interfaces, but I can give you a deeper look in the block diagram on the next slide. So, as you can see from the block diagram on the right, we have these three different separated power domains, and every power domain has its own interfaces. So, like with the 7-ULP, we have UARTs, I2C, SPI at the application domain, but as well as on the real-time domain. But new for this 8-ULP is, for example, the CAN interface and also the Ethernet interface. Also at 7-ULP, the USB was limited. There was only one USB, and yes, for some application it was not enough. with 8 ULP we have now 2 USB interfaces. And the idea between our module, which we call solder core 8 ULP, is to bring all the features of the CPU to the customer via this LGA contacts. And on the module itself, we have the 8 ULP for sure, but also we have low power DDR4. We have i.MX interface, i.MX memory, so we can put a i.MX flash drive directly on the module, and we have the power management controller directly on the module. So to summarize it, on the solder core 8 ULP, we have the 8 ULP processor. It's a combination of Cortex A35 and Cortex M33. The module is available with 1 or 2 Cortex A processors. It runs up to 1 GHz, so more speed compared to 7 ULP. The L2 cache is double from the 7 ULP. We still offer a tested Yocto BSP, a real-time FreeRTOS and bare metal BSP, and we have also a real-time communication stack which for communication between the Cortex A and Cortex M. And we offer extensive display support like MIPI, DSI, LVDS and RGB. The module is again available in 2 temperature grades. The commercial grade is 0 up to 70 degrees, but the industrial grade now goes from -40 up to 85 degrees. The module and the CPU as well are long-term available until at least 2032. So, and to make it easier for our customer to use this module, we develop a complete solution, yes? So we go one step further compared to the 7 ULP solution. Means we make a package, yes? So we have a special 7-inch MIPI DSI display. On the back of the display we have a carrier board directly on the display, and on this carrier board is soldered our modules, the solder core 8 ULP module. So it can be used for the first steps for starting, but it can also be used in real applications. So some of you are asking, so what are the use cases for such a solution? So Patrick, can you say some words about possible use cases?
Yes, for sure. Thank you, Holger, for the explanation. So I think it's very interesting for some customers to use the complete solution and can integrate it in their own product directly. Yeah. So we have thought about some use cases for the 8 ULP, what we can do with this CPU and the product from F&S. So one thing is the use case, the low power LCD application. So we can see here in the graphics 3 different stages. We have on the left the user interaction state. So it means full performance. We see that the audio video domain is running and also the application domain is running. The real-time domain is in idle mode in this state. So the user can interact with the display, and the display will refresh itself with some necessary information, for example from the cloud or something like this. And if the user doesn't use the display itself, then the display, we switch to the next stage, it's the display information mode. So, and we see what's changed, the audio and video domain still runs. That means the display is still running, still active. but the application domain is shut down or in idle mode, and the real-time domain runs. So now the display information will also be refreshed, but we don't have, for example, network access, cloud access, so it's just some basic informations will be refreshed, like for example the time, for example. So, and this is the display information mode. So we are, like you see in the graphic, it's partial power save mode. And then we have the deepest mode. For example, if the customer just doesn't interact with the display about some time, like 2 minutes or something like this, then we go in the deep suspend mode, which means all of the domains are still in idle mode or sleep mode, and the display is off. So now the customer can interact or wake up the system, if, for example, with a motion sensor or something like this, and so we can switch between these different states. For this state, so we have also a different power consumption. So I mean, I think it's clear in the full performance mode we have the most amount of power what we needed, but for the display information mode we have less power consumption because the application domain is shut down. And I guess this will be the most, it takes the most power in this state. So if we just run in the real-time domain, we doesn't need so much power, and therefore we have a better power consumption. Mm-hmm. So okay. I think we can go to the next use case. We have another use case. We think about low power voice recognition. So I will compare this maybe a little bit to the system from Amazon, Alexa. So we have on the left side the full power save. There will be just the key phrase detected. And on the right side we have the speech processing, which means full performance. So it's like the Alexa from Amazon. You just have to use 2 keywords, either Alexa or Echo, and then it wakes up, and then you have the full speech processing. So, and this is also what we can use it for, because we have in the real-time domain a Fusion DSP unit. And this unit can be used for detect some key phrases, for example, and there we can just use maybe in this case hello there, and then the system wakes up and goes to the full performance mode, where we have then the audio video domain and also the application domain, and then we have full access to the different units for speech recognition, voice recognition, and then we can get some sentences, send it to the cloud to evaluate it and get the answer back. And we have another use case, the low power edge AI computing. We have here the 3 domains. In the middle we see some units, some frameworks I would say, for example the TensorFlow Lite, Glow, and other frameworks which are all supported for this CPU. And here you can see just how these frameworks and units are splitted through the domains, through the different domains. So on the left we have the real-time domain, where we can just use the CMSys NN unit, or just TensorFlow Lite directly on the M33 for, I would say, low power operations. And then we have in the middle the audio and video domain, where we can use also TensorFlow Lite or just the Glow unit. We have OpenCL, because we have there the Hi-Fi DSP unit, and we also have the GPU there, which we also can use for some of these operations. So, and on the right in the application domain, this is the high performance mode, I would say, where you can do the most operations in a fast time, I would say. Then we also have the TensorFlow and the ARM-CL unit, also ARM-NN. So I guess that's also interesting because we can just separate tasks of this AI computing, and therefore I think you can just split these tasks to the different units compared to the operation itself, and so that's also, I guess, very interesting for the future.
Okay, so thanks, Patrick, yes, for this explanations and the explanation of the use cases. So yes, we have heard now a lot of information about the two ULP processors from NXP and the corresponding F&S products. And so we come to the end, and on the last slide I want to compare the 7 ULP, 8 ULP and the 8 Mini, yes. So because I think one of you are asking, yes, 8M Mini, for example, it has up to 4 Cortex-A53 and has also a Cortex-M4 inside, so why should I use 8 ULP or 7 ULP, yes. So because of that we have done this comparison, and yes, let's start with the cores itself. So as you can see, at 7 ULP we have one Cortex-A7, so 32-bit up to 720 megahertz, yes, and for sure I have to say this is not very powerful, yes, so compared with 8 Mini. But if we take now a look to 8 ULP, we have now two Cortex-A35. So it's not so powerful as Cortex-A53, yes, not as 4. But I think for many applications, yes, it's enough, yes. So and also the speed increased from the 720 megahertz now to the 1 gigahertz, yes. So for the real-time core, for the Cortex-M, at 7 ULP as well as 8 Mini, we have the Cortex-M4. With Cortex-8 ULP, we have the Cortex-M33. So more processing power at the real-time domain, at the real-time application, with 8 ULP. Yes, RAM memory. So for all boards we are using a low-power DDR4 because of saving power, except 7 ULP where we use low-power DDR3. Yes, so but also low-power memory devices. Display camera. With 7 ULP we have 2-lane MIPI DSI display, so we are limited in terms of resolution of the display. With 8 ULP and 8 Mini we have 4-lane MIPI DSI, so we can connect really high resolution displays to both CPUs. Also, 8 ULP and 8 Mini have MIPI CSI for connecting a camera. Domains, so power domains, yes, separated power domains. 7 ULP was the first CPU with 2 separate power domains. With 8 ULP, the concept is improved with this additional audio-video power domain. With 8 Mini, which is not directly targeted for low-power applications, we have only one power domain. So the leakage, if you only run, for example, the Cortex-M, is higher compared to the 8ULP or 7ULP. The graphics, it was always the intention from NXP with 7ULP and 8ULP to have good graphics, yes, attractive graphics for the applications. So 7ULP as well as 8ULP both have 2D hardware acceleration and 3D hardware acceleration. With 8ULP it's enhanced, so we have OpenGL ES 3.1 and OpenCL and Vulkan. So it goes over that what was offered by ADEM Mini. Interfaces, I already mentioned this. With 7ULP we have only one USB, so that's yes, not much. It's sometimes critical, yes, for example, if you have a PCAP attached with USB and then want to have an USB plug for a USB stick, for example, yes, or a USB device for connecting to your tablet or something else, then it's limited. With 8ULP as well as ADEM Mini, we have two USB OTG on-the-go ports. With 8LULP, we have now also 100 megabit Ethernet. Yes. I think for many applications it's enough, yes. And also a CAN interface. So ADEM Mini has no CAN interface, but with 8ULP we get one.
Yeah, we don't have a regular one.
Yes, so let's say on the CPU with the ADEM Mini we don't have one, but on the F&S solution, the PicoCore ADEM, we added an external CAN chip, yes, besides the CPU, so we offer also on the board CAN, but from the CPU itself we don't have it, yes. So power management. Power management with 7ULP is done in the Cortex M4. With the 8ULP, there's an additional RISC-V chip within the CPU, so which is dedicated for the power management functions. Security, 7ULP and ADEM Mini, both, or 8ULP as well, all offer the high assurance boot, so signed boot, encrypted boot, and such things. But the 8ULP has already the new secure enclave. So yes, there's again an additional RISC-V CPU inside of the CPU, and this RISC-V is dedicated for the security functions. So it has his own ROM code, and it cannot be accessed, yes, from the other cores in the CPU. And the most important point for the 7ULP and 8ULP, the power consumption. We have heard from you, 7ULP around 11, 12 milliwatts. With ADEM Mini, we have done the same measurements, and is 10 times more compared to the 7ULP. 8ULP, we don't have measurements up to now, but we expect better values compared to 7ULP. So I think really interesting solutions, low power. I think everybody today has to think about saving energy, yes, in every device. We have to keep our eyes on the environment, yes, on our environment. We have only one. And so this can be these solutions can fit very well in every device where we have to save power.
Yeah.
So thanks a lot for your time and your interest in our presentation. If you have questions, please don't hesitate to contact us. We are here for your questions, and see you next time.
Bye.
Bye.